Alright, pretty big video this one. We are looking at transformations in the complex plane. So before we begin, I think what we'll do is we're going to do a review, a real review, so a review of how graphical transformations happen in our Cartesian plane. So the first big thing we learn when we're quite young is that if we replace x with x minus a, it translates your graph to the right. If we replace y with y minus b, it translates up by b. If we replace x with negative x, it reflects in the y-axis. If we replace y with negative y, we reflect in the x-axis. If we do two replacements, so if we replace y with negative y and x with negative x, that is a 180-degree rotation around the origin. If we replace x with negative y and we replace y with x, that is a 90-degree clockwise rotation about the origin. These are quite fun to play with on Desmos. If we replace x with x over k, it scales the graph by a factor of k in the x direction, and that's very similar with y, just scales it in the y direction. Replacing both y and x with their scaled versions just scales the entire graph by k, and hopefully you guys, this isn't going off the screen. If we swap x and y, it reflects the graph about the y equals x axis. So it looks like a lot, but that's just all of the transformations that are happening in the reals or in the Cartesian plane. So what we want to look at now is how do transformations work in the complex plane. So first thing we'll do is we're going to go through and we're going to match all of these up, just like what we've done in the reals, with the complex. So we're going to represent our general complex equation, f of z, because z is our standard variable that's standing for complex numbers. So z is x plus I, y. So it's a variable point, and we've got some function that is mapping that variable point. So we're going to represent the roots of the general complex equation, f of z equals 0, where that is f of x plus I, y equals 0. So if we replace x with x minus a, well, that's a translation to the right by a. What does that mean? It means that we get f of x minus a plus iy equals 0, and you can see that that's just f of z minus a, because you've got x plus iy minus a, so it's just z minus a. So all we have to do is replace z with z minus a. Okay, replace y with y minus b. That translates the graph up b. So what does that look like in the complex plane? F of x plus I, y minus b, that's our replacement, equals 0. Well, that's the same as f of z, x plus iy, minus ib. So in short, to translate up b, replace z with z minus ib. Okay. Replacing x with negative x reflects in the y-axis, but how can we do that with z? So replacing x with negative x, well, that there is simply, so negative x plus iy, that's simply the negative conjugate of z, isn't it? Because the conjugate of z would be x minus iy, but it's negative x plus iy, so just a negative conjugate of z. So if you want to reflect in the y-axis, just replace z with negative conjugate of z. Next transformation, we're going to replace y with negative y, that reflects in the x-axis. But how do we do that to z itself? So that's just going to be f of x minus I y equals 0. And that is the conjugate of z. So to reflect in the x-axis, just replace z with the conjugate of z. Next, if we replace x with negative y and we replace y with x, that is a 90-degree rotation, but we want to just manipulate z, not do these two parts. So let's do the replacement. We get f of negative y plus ix equals 0, and that is just I times z, because the I multiplied by I, it's going to give negative 1 times y plus I times x. So if we just replace z with iz, that is a 90-degree rotation. Those of you who have done a bit of matrices and stuff might start to make some connections with rotational matrices. Okay, there's a couple more to go. It's quite a bit of stuff. So replace x with negative x and replace y with negative y. That is a 180-degree rotation. So there's our replacement, f of negative x minus iy, and that's just negative z. That's quite intuitive. So if we replace z with negative z, then we rotate 180 degrees. Okay, scaling. If we replace x with x over k, that scales by k in the x direction. There's our replacement. F of x over k plus iy equals 0. Now this is a bit of a more complicated one. So note these two things here. So note that z plus z conjugate is 2x and z minus z conjugate is 2iy. That shouldn't be too hard to prove. That means that if we want to write x over k plus iy just in terms of z, well, x is z plus z conjugate over 2. So there's our z plus z conjugate over 2k. Plus, we have y equals z minus z conjugate over 2i. And your i's cancel out. So that is what we have to do there. If we want to scale in the x direction, that's probably the trickiest replacement, is we need to replace z with z plus z conjugate over 2k plus z minus z conjugate over 2. And I'll just give you the y scaling. So y scaling is exactly the same, except your 2k is under the difference between z and its conjugate, instead of under the sum of z and its conjugate. And if we want to scale both, it's actually not too bad. Just replace z with z over k. Hopefully that makes sense. So that's, I think, almost all of the, that's all of the transformations in the complex plane. I recommend maybe going through those, maybe trying to prove a couple of those, maybe especially this one, maybe just work your way through replacing x with x over k. But we will do an example. So what if we want to rotate a graph in the complex plane? We want to rotate the function f of z about some unknown point a plus bi. Well, the first thing we need to do, I'm just to make this video a little bit more fluid, I've pre-written a lot of this stuff. So first thing we want to do is we want to translate to the origin. So we're going to replace z with z plus a plus ib, because that's going to move down and left. So it's going to move us from this point, a plus bi, it's going to move us back to the origin. Now that we're back at origin, now we can rotate by 90 degrees, which means we replace z with iz. So there's our replacement, our total replacement. So z has become iz plus a plus ib, and now we want to translate back. So now we're going to replace this z with z minus a to move right a, minus ib to move back up b. Or you might want to think of it as z minus a plus ib. So z becomes this messy thing, I times z minus a plus ib plus a plus ib. So overall, to do this, rotate 90 degrees about a plus bi, this is what we replace z with, iz plus a plus b minus I, a minus b. I recommend you guys work your way from this one to this one. It's not too bad. Maybe just expand everything out and simplify. So can we apply this to a more real example? And we can. So we want to apply this above transformation to this line. So this is called a locus, or loci of a complex point, and it's given to us as the absolute value of z minus the absolute value of z minus 2, and that's equal to 0. So this is the line, and I'll show you this at the end of this video. I might go through why that is a line, but I just want us to focus on this transformation. So first of all, we want a, which is 2, and b, which is 1. So now we can just apply this formula. So we're going to get iz, iz, stylize that I a little bit, plus a plus b, minus a minus b, which is 1 I. Okay. That is what we're going to replace z with. So we get iz plus 3 minus I, replacing that one, minus, replacing this z, iz plus 3 minus I, still minus 2, all in absolute values. We could tidy this up a little bit. Iz plus 3 minus I, absolute value, minus iz, what have we got here, plus 1 minus I equals 0. Okay, so then we're going to have to kind of think about what this might look like. I'm going to do a little trick. I'm going to multiply through by the absolute value of negative I. So you're going to have to go back, remember your absolute value algebra steps, okay? And that's going to give us z minus 1 minus 3i minus an absolute value z minus 1, then what have we got, minus I. Just because we just don't want to have so many i's in there. So that's a nice little trick. Multiply through the absolute value of negative I, and that's going to just remove some of those i's and put the i's on the constants instead. Okay, so what does that transformation look like? So I've drawn it up here. So this is our original line, the green line. Absolute value of z minus 2. And we're rotating about this point here, which was 2 plus I. So maybe if I got my ruler and we rotate around this point, you can see 90-degree rotation. It's going to take that line and put it there. Hopefully that's a good enough illustration of how that's happening. Okay, that's basically the end of the video. I might just quickly show you in fact why that is the straight line. So I'll just use the back of this paper. So we're looking at how how do you know that this is a straight line? I'm just going to do it algebraically. So obviously the absolute value of z, where z is a plus bi, is a squared plus b squared, all square rooted. Now this z though is a variable complex point, so it's in the form x plus iy. So this is just going to become x squared plus y squared, all square rooted, minus the absolute value of z, which is x plus iy minus 2. So that's just x minus 2 is the real part. I'll put that in brackets even though it doesn't need to be. And so just like absolute value, we're going to square the real part. X minus 2 squared, and we're going to square the imaginary part, and that is all square rooted. It's still equal to 0. We can add this to that side and square, so that x squared plus y squared is equal to x minus 2 squared plus y squared. So I've added this and squared both sides. Y squareds are gone. X squared is equal to x squared minus 4x plus 4. X squareds are gone. 0 is 4x plus negative 4x plus 4. X equals 1. That's why this green line goes through 1. And if you were to do the difference of absolute values for this graph, it might be a nice exercise for you to have a go. You should get the line going through 2i. Okay. Whew, that's quite a lot of transformation geometry. I recommend maybe going through this again, maybe trying to work some of those little bits and pieces out. Tomorrow's video, we'll be going through more of this sort of stuff. Loci, it might get a little complicated, so you want to have a really nice understanding of these transformations. Awesome.